Hello everyone, I'm Yumeka. Today I'm going to talk about autonomous task scheduling for Earth observing satellites tracking moving targets with low maneuverability. So first, thanks to my co-author and PhD advisor, Dr. Schaub, for supporting my research in this paper. So the problem we are looking at is Agile Earth observing satellite scheduling problem. Agile meaning satellite can maneuver along and across the orbit of Earth, and Earth observing satellite is satellite with imaging capability. Scheduling problem is to find the best action to maximize the reward for image target. With the increase of the target request, it is really important to find the good solution or good algorithm to solve this problem. The human primate plan is probably not optimal. That's why we are introduced reinforcement learning into this problem. So for the location of uncertainty, we include this into this problem, but why? Traditional scheduling, we assume fixed target with perfect location knowledge. It's completely fine if you want to look at Orlando, Boulder, or those fixed target. However, if you want to see moving target like ships, plane, wildfire, tornadoes, those natural disasters, then there's a problem. You need to consider target location uncertainty. Otherwise, if you point your estimated location, but it's actually not there, then you need to consider some kind of searching algorithm method to actually capture those kind of target effectively. And also real-time responses is really important for that kind of problem. And that's why reinforcement learning is very good, because once you train the policies and evaluation is pretty quick. So with that, let's modeling the location uncertainty. We have the search area with the center of the search area is estimated location with some kind of uncertainty around that, like a standard deviation, and you define the search area. Then we assume the scanning maneuver, like you can see in this figure. Then we also define uncertainty, normalized search area, and acquisition speed shown as V in the figure. And scan width and search duration is the time to spend scanning whole the area. And from that, true imaging time is sampled, and the sampled from the Gaussian distribution, and the mean is the searching duration of the half of the search duration, because as I said earlier, the center will be the high probability that's there. So the half of the search duration is high, most likely. And even you spend all the search duration, you still have 5% chance to miss the target to capture more realistic scenario. And also we made a simplification. This is a big assumption that in our simulation, we don't actually simulate that kind of scanning maneuver. Instead, we just pointing the center of target for the true imaging time. Then we consider the imaging is successful. So with that, this is a problem looks like to visualize, and I'm so visual person, so it's pretty good for that. And target size is showing the search area. Target color is represent priority, and green is low, red is high. And once the target is imaged, it turns to blue. And with that, to solve the problem with reinforcement learning algorithm, we need to formulate, and we use partially observable semi-concrete decision process for formulation. And state space is all the information to propagate simulation forward, including satellite and environment states. And the observation space is part of a state space, and it is used for decision making for agent, including satellite dynamics, as well as the 32 upcoming target information. If observable, the uncertainty is part of that too. And action space is upcoming 32 target imaging actions, and transition function is deterministic and propagated from BSK-RL simulator, which I'm going to talk in a bit. And as I said earlier, to consider as image successful, you need to meet all the three conditions. Pointing angle, angular rate should be within a threshold, and those two should meet for true image time. And the last component for POMDP formulation is reward function, which is very important to define the metric for this problem. And we consider two different ones, but it's pretty complicated if you see just equations. So let's break it down. So first one is weighted uncertainty. We call it MATRA because priority of image target times uncertainty of image target. So if you visualize it, it looks like you're going to find the perfect target, high uncertainty plus high priority. In contrast to that, additive uncertainty reward function is priority plus lambda uncertainty. Lambda is the tuning parameter balancing between priority and uncertainty. And if you visualize that, it looks like different trend compared to multiply. And if you increase the lambda, it means that you think uncertainty is more important than priority. And if you think the multiply is trying to find perfect target, then the additive is more like even you're not very good for either priority or uncertainty, I will give you partial credit. That kind of intuition. And also we have two different reward assignment strategy. First one is unique target imaging, imaged all the once the target is imaged, then the target is removed from the list so that you will never be able to take it again. However, the multiple target imaging, you are allowed to do re-imaging. So keep all the target in the candidate list so that you can take it again in the future. So let's move on to the simulation setup. As I said earlier, that we use BSKRL for spacecraft scheduling environment, which consists of gymnasium, reinforcement learning environment interface, and replace the environment with BASIC, which is high fidelity fast spacecraft simulation framework that our lab has developed. And with that, we use the PPO algorithm for reinforcement learning. And let's move on to the first experiment to see what kind of training environment and uncertainty information affect to the performance. To investigate that, we train three different policies. And the first one is baseline, and this is used traditional scheduling method. So once you settle into one target, then you're immediately able to take the image and no search assumed, but test it in the true imaging time environment. So that's that shows how important to train more realistic environment. And for observation known and observation area, those differences are pretty obvious that if you can use the target uncertainty information for the decision making. So as an uncertainty information search area is used for that. And we made three additional assumptions for this experiment. So search area is initialized at the start of the episode and remain fixed for whole episode, which is 3 orbit. And reward depend only on target priority, not consider uncertainty for now. And each target can be imaged only once, so unique target image is assumed. With that, let's move on to result. And you can see the result plot that we deployed each policy into different number of target requests, 1,000 to 10,000. And you can easily see from left reward plot that observation area performed the best and observation none is next and baseline is the worst. Why baseline is the worst? Because they don't know it takes time to image. That's why they don't have enough time to complete the search. Then even you choose the target, you don't have time. That's why image success rate is very low compared to other two. But what's the difference between observation zone and observation area? Those two differences is what kind of target you're getting. So observation area focuses more on the low uncertainty target because it increases more chance to complete the image, and also you can take more image if you choose low uncertainty target. However, the problem is this good policy, because if you don't take the large uncertainty target, and then it's the uncertainty might increase more and more over time, and you will never have chance anymore to take that. That's why we're investigating reward function analysis next. So in this experiment, we consider re-imaging, and also target uncertainty increases over time if it's not imaged. So this is the same problem as previous, and once it's imaged, you know exact location, so uncertainty goes to 0, but keep the target into the list so you can take it again later. And if the target is not found, then the uncertainty grows over time, and the expansion speed is about the ship speed. We consider pretty slow target first as a first step. And with that, as a reminder, reward function, we consider two different ones, multiply, additive, and the lambda is a tuning parameter to balance priority and uncertainty. And we try several different lambda for this experiment. As you can see, 0 to 5 is used for the additive tuning parameter. And you can see the result plot, the sum of the image priority on the left and sum of the image target uncertainty on the right is all the episode and average over all the testing case. And as you can see from this figure, when lambda increases, priority goes down and uncertainty goes up. It's expected, right? If you increase lambda, then you take the uncertainty more seriously. So it makes sense. And the green, which is multiply, is kind of middle, balancing between those two metrics. So what's a good policy then? So then look at deprecation, because if you take the same target image again and again, it's probably not the best, right? So that's why showing here is deprecated target. If you choose the lambda equal 1 or less, then it takes so many same target. So it's probably not a good idea, right? But it's also depending on when it's happening. If you take the target and same target right after, or maybe one orbit after, then it makes sense because the uncertainty grows over time, right? So when the deprecation happen? So as I said earlier, if the current orbit, it's immediately after you take image, it takes the same image again. So you want to avoid current orbit deprecation. So less than 1 or less than 1 lambda is probably not good. However, if you use larger than that, 2, 3, 5, and multiply, seems like similar performance. But what kind of difference you can see? Let's summarize those policies. So multiply, strong focus on high priority with high uncertainty. So it's only get the perfect or very good target. However, additive, low lambda, if you find the high priority target, you take that a lot. I like it, so take it. That's probably not a good idea, right? So finally, additive high lambda case, it's uncertainty-driven behavior. So it's explore a broader target than compared to multiply or additive. So even the target have a little bit less priority, it takes the image if the uncertainty is large. that's additive. So depending on your mission objective, you might want to choose from multiply or additive with high lambda. So with that, to conclude my presentation, I investigated the aerial-based satellite task scheduling under target location uncertainty. And first experiment shows that training in the realistic environment with uncertainty observation is very important for the performance. Also, reward design matters. We investigated 2 different reward function, and depending on mission objective, you might want to choose different one. And finally, the future work to cover all the Earth's surface. It is more interesting to see the multiple satellite cooperation scenario, as well as the biggest assumption we made. The search imaging maneuver is not considered just looking at the center, which is very big assumption. And if we actually simulate those kind of scanning maneuver, then that will be very good future work. With that, thank you so much for listening to my presentation. And if you have any questions, happy to answer. So feel free to contact me, and you can see the buses and BSQ RL QR codes. So if you're interested in, please scan. And yeah, thank you so much for listening.